right, so we're talking today about our spectrophotometry, our idea of using color, the idea that the color changes with transitional metals in a redox reaction helped us understand when that chemical absorbed enough information, or in this case, electrons. In our previous lab, okay, we had the permanganate ion, MnO4, negative. Okay, we've already talked about that this guy, this transitional metal right here was +7 in this ion. And during the redox reaction, it was able to absorb 5 electrons, okay? And this is what you did in your lab. You wrote the balanced redox reactions, and you got Mn +2. And we use the color change in this scenario to our advantage. Remember, this was a purple color. And remember, if there is a color associated with a chemical, whether it's a dye or a solution, it's because that chemical's electron arrangement is such that it can actually absorb photons of light of certain wavelengths. Meaning, white light is made up, it's hitting me right now, of all the wavelengths, all the different colors, okay? And the reason you see white is because there's a reflection back of all those photons in your eye, all those different wavelengths mixed together. Now, if you do see a color, it's because the chemical arrangement or the electron arrangement is such in a certain chemical that it can actually take in certain amounts of those wavelengths as energy. What it doesn't take in is that color. Now, very simplistically, okay, what we have is a nucleus. Has a number of protons. We should know that Mn has a unique number of protons. The proton number is what identifies an atom. We'll talk more about that. But in simplistic case, we know that there's energy levels for electrons, okay? And electrons can exist either closer to the nucleus or farther away. And we're going to learn, okay, that existing farther away is a higher energy state. And if you think about it coulomically, these electrons here that are close to the nucleus feel the nucleus more because of distance. Where am I going? Gosh darn it, Coulomb's law again. Okay, how many times do I have to draw it? But this whole course can be defined by it. So if the distance between these electrons in the first energy shell or principal energy level, we'll get to those specifics. If the distance is really small, okay, really small, if you make your denominator small, what happens to your force of attraction? Or if I do arrow down, a really small number. As you make the distance between positives and negatives, remember this is the positive, this is the negative charge, they're both +1, so that's not the factor here. The factor is distance, proximity to the nucleus. So electrons that are closer, okay, I hit record, right?
Yes.
Okay. I feel like okay. Electrons that are closer, okay, have a higher force of attraction to the nucleus. That makes sense? Sure. If you were to hang out with your mom or dad, let's say your mom is going to follow you around to class all day. And I know you love your mom is there to support you, but I'm sure you'll act a little differently. I can imagine, okay, you guys would be dancing on the, probably would curtail a conversation or two, or you won't laugh as much about something, okay? You'll act differently, okay? I bet you'll act with lower energy. I know Dan would be dancing on the tables like he normally is, okay? But the point is, you're gonna act differently. It's just normal, okay, Mom? Yeah, all right, Mom's with me today. Now, if you're farther away from Mom, hey! All right, say, okay, hi, yeah. You got a little more energy. Not that you're gonna be crazy and just go nuts and run out of the room for no reason and scream, I want candy, okay? But you're gonna have a little more flexibility in maybe what you laugh, do, or say. Not that it's wrong, it's just that you are not being watched, okay? So the farther you are from the nucleus, hey, the distance is greater, that force of attraction is less. So electrons that are closer are more controlled. They have low energy. Electrons that are farther away are less controlled, less They have higher energy. So for electrons, arrangement, if electrons can move to a higher energy level, they must absorb energy of a certain amount. It's not a little bit, a lot, it's an exact amount. It's called quantized. We'll talk about that. So, to go to a high energy level, you must absorb wavelengths of light. Now, normally, chemicals that are colorless, it's hard to write with a colorless pen, so I use a black pen, sorry. I'm not sure if that's purple. Is that purple? Is that purple?
Yeah.
Yes! All right, I wasn't sure. It could have been blue, but I'm happy. So here's colorless. So if you're colorless, let's get rid of Coulomb's law, okay? Here's the deal, okay? We've got an electron arrangement where the electron jumps are really huge, meaning wavelengths of light, visible light. We all know visible light has what? Very low energy. Because if it didn't, okay, I'd be knocked over, I'd be dead right now, okay, from the high energy light. Turn the lights off, okay? We don't do that. So this leap is bigger, okay? And I'm just giving it as an example. So lower energy to higher energy. So in order for this chemical, which is colorless, okay, to absorb wavelengths of light, it needs more energy. And guess what? Visible light does not provide enough. So it doesn't absorb visible light. Now it can absorb other types of energy that's higher energy. Maybe UV radiation, maybe what? Gamma or X-rays, absolutely. So what is happening here that creates a scenario where the leap is small enough so that light, small energy of light can make that leap? Crystal field splitting. The idea that this has a high positive charge that can draw in ligands. For us, the ligands are water. Okay, so that's really important. Now, what do we know about these elements? These elements that can draw things in, back to Coulomb's law, sorry, F equals a constant, R1, R2 over D squared. First of all, transitional metals tend to have high charges. And because they're transitioning into smaller atoms going across, they start off smaller, so when they become positive, their distance or their radius is small. That creates a high force of attraction. In order for transitional elements to have a color, okay, they must be at a high enough oxidation state and be small enough to have such a high force of attraction that the ligand, that's the chemical that's negatively charged or has some electrons, gets forced into the positive, not just attracted. And, this is the key, you must have something called d orbitals. Okay? You must have d orbitals. So, if I look at something called my periodic table, okay, and excuse me because I need to do some cursoring, all right? So I go to my periodic table that I just, where's my cursor? There we go. I wasn't. Okay, where are you? There we go. And go to my periodic table. Okay, what do we know? Okay, well, the elements here have d orbitals. We're going to learn that 10 electrons can exist in a d orbital. Okay, these have end in s, these have p, and these are f. Something we'll talk about. So when I deal with electron configurations, okay, and let's deal with nickel right now. So if I stop at nickel, all right, let's do the configuration of nickel. All right. Now again, color is due to the fact that we have such a high attraction, electrons are pulled into the d orbitals. So to have color as a solution, you have to first have these d orbitals. Now remember, not all of them get pulled in. The ones that get pulled in directly in the same plane destabilize some of the d's. There's 5 of them. Okay? So some get pulled in directly. Remember, 6 water molecules will surround this highly positive ion. Okay, because of them repelling each other, as electrons repel, they'll find an equal distance area to attack. But some will attack right in the same plane where these wave functions, where electrons exist for d orbitals, and some will go in between. The ones that go sort of right through, because of the high attractive forces, okay, will create a split in the d orbitals. And normally we write the orbital notation where electrons exist like this. All the d orbitals are the same energy. This is an energy diagram. But because of crystal field splitting, with 6 anyway, 2 will become higher in energy. And that, my friends, is your small gap. Small enough that visible light can make an electron jump from this to this. If the gap is too big, visible light can't do it. Okay, so to have color, you have to be a transitional element that has d orbitals. Okay, 2, okay, is you have to have a place for electrons to go and a high attraction. So let's write the electron configuration of nickel, okay? And again, this might be something, we're going to revisit this. But to get to nickel, okay, atomic number 28, I have 20 electrons. This is going to be 1s2. It's okay if you don't understand the s and p's right now, but just stay with me. 1s2, okay? 2s2. The 2 means the next energy level. The s is the type of orbital, okay? 2p6. We're still in the second energy level, but I have p orbitals. Notice there's 6. 2 pairs go into an orbital. That'd be 3 boxes if I did the p's. So 2p6. Oh! 3s2. I'm in the third energy level. Getting farther away as I add numbers, okay? In the third energy level, 3s2. We call this the s block. And we'll talk more about this, okay? Okay, 3p6. Okay, now 4s2. Now this one's a little weird. This is actually 3d1, 2, 3, 4, 5, 6, 7, 8. 3d8. Notice 10 fills it. Okay? Now, so why does the 3 come after the d? Well, it just so happens there's overlapping. The fourth energy level starts before the third ends. So there's kind of overlapping here. We'll talk about that. But the key here is 3d8. Now, if I put the electrons in for nickel, here, watch what I do here. 1, 2, 3, 4, 5. The first 5 are going to fill 5 of the orbitals. Orbitals or pairs can exist in the d. Why? Because electrons repel themselves. Why would they go in the same place if they repel themselves? 5, 6, 7, 8. So what do I have? These guys have 1. Now, I've got these other electrons from the ligand being pushed sort of in. That's what creates this repulsion, higher energy state. But guess what, party people? Is there room for another electron to move up here? Yeah, there's room for electrons to jump, but they'll only jump if they absorb an exact amount of energy from a certain type of photon, okay, red, blue, orange, that has a certain exact amount of energy. If this gap was too big, it'd be colorless, but this creates a small enough gap that this doesn't have naturally. Well, crystal field splitting means that I'm taking the d sublevels and I'm splitting them to create a gap. So nickel has color, okay, when it's in its +2 or +3 state, okay? Now, you don't have to know exactly what state. We've been using this color change. All right, let's do zinc, okay? Same idea. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d what? If this was 3d8, this is 3d what? 10. That means what? They're all filled. Does that mean there's no crystal field splitting? No, there's still a gap there. Clearly, if I've got zinc +2, who's what? Pretty small, it's going to pull in 6 waters. But because these are all what? Filled, is there room for electrons to leap there? No. So electrons can't leap, can't absorb wavelengths of light. So what is the color of zinc? Colorless. And in fact, because it can't do this, we consider this column not to be transitional metals. To be a transitional metal means that you have some unfilled d orbitals for electrons to move. Okay, that's some hints for your form tonight, all right, that people had some issues with. Okay, and you'll get a better feeling for that as you continue on. All right, now, a couple of little things here. Now, when they have color, the charges have to be high enough to be pulled in to create these gaps. That's important. Let's go back to the lab that we previously did, okay? And the first time we talked about this obviously was in our redox lab. I picked MnO4 negative because number one, strong oxidizing agent, but two, it's +7, pulls in the waters, creates small gaps. It's purple because it absorbs what? It's purple, okay? It absorbs,
Everything.
probably absorbs the green part of the spectrum, right? Think of this, party people. Roy G. Biv. Red, orange, yellow, I can do this. Green, Roy G. Blue, indigo, violet. I mean, there's more colors than that, but those are the general colors of the rainbow. Low energy to high energy. So if I am seeing purple, which is made up of what? Two colors, right? Red and the blue part of the spectrum. I'm guessing, and it's a rough guess, that it's probably absorbing part of the green part of the spectrum. And therefore, it's not using the red and the blue part of the spectrum, okay? So that's kind of the opposite of why grass is green, chlorophyll, okay? Although it's not made of a transitional element, its coloring is different, okay? But it uses the same negative theory. It's green because why? It's UC green because it absorbs the red and the blue part of the spectrum. One of the other questions you guys as a group didn't do so well on, okay? But back to reality, okay? Up there goes gravity, and I'm rapping. Okay, in order to do the redox lab, where am I? I'm trying to curse it here. In order to do the redox lab, I had to make a solution of Fe+2. Okay, that was my standard, so that was a solution like our KHP to standardize the strong base. Well, we used Fe+2. Let me explain. So, this is really reactive, it drove reactions, but the whole purpose of the redox titration was to know this concentration to answer something about the other. That's what a titration is. But I wasn't so sure about its concentration because it reacts with things in the air. Okay? So, what we use is Fe+2 solution. And of course, it's going to oxidize, okay, give off an electron to become Fe+3. Now, what's really cool is how this all connects. I had to make this fresh daily because if I have Fe+2, it's clear. 24 hours later, okay, if we were in that, what was that, SpongeBob? 24 hours. So it's color changing. What? What's going on here? Fe+2 is becoming Fe+3. Okay? Something inside the flask was pulling electrons from the Fe+2. Anyone guess what that could be? What? Well, water. What's in water? Oxygen. Or in the air?
Carbon dioxide.
O2. How strong of an oxidizing agent is O2? Absolutely. Okay. So the O2 in the air, okay, was, remember, what is it? It's an oxidizing agent. Itself gets what? Reduced. Okay. So over time, this was becoming Fe+3. But we're going what? To a color. Colorless to a color. What's happening here? What charge is this? Fe. And over time, this is becoming. Why is the color developing? The charge is increasing, which is doing what? Making the force of attraction between the oxygen end of the water do what? Increase enough for those electrons to interfere with the d orbitals of iron. So there you go. Mn+7 has color. Mn+2 doesn't. Why? The force of attraction isn't great at Mn plus 2. The force of attraction at Fe plus 2 isn't great enough, but Fe plus 3 has a color. In fact, let this go, this becomes a bloody orange color, okay? And our reddish maroon color of our blood is due to the Fe plus 3 that's surrounded by 4 ligands, not water, but hemoglobin, okay? Bigger molecules that helps us deliver oxygen. Things are interconnected. By the way, your blood is never blue, okay? I know some people think that. Well, it's blue when it hits oxygen. Okay, then I had one person like 5 years ago scream at me and say, it's blue. I see it blue here. Well, it's because your skin, if you're seeing blue, it's scattering the blue. Blue has higher energy. We'll talk about Rayleigh scattering in our light part of our course, okay? But if you ever give blood, does it come out blue? There's no oxygen in the syringe, okay? So, okay, any case. All right, so that's my little review of spectrophotometry. You guys can tune out now and go to the homework and watch the video and go from there. These guys are going to have that homework tomorrow night. We're going to get into the lab, all right? So hope those hints were more helpful enough. Try another round of submissions, and if it still doesn't go well, we'll do it again. And I kind of like this kind of stepwise submission of that form.